Okay, so welcome to the next talk, everyone. The talk will be given by Farid Shahandeh, who's at Swansea University. He's a Royal Commission for the Exhibition of 1851 Fellow there. So he's going to talk to us about contextuality in GPTs. So I'll hand it over to Farid.
Okay.
Ready?
Thanks for the introduction. And yes, okay, contextuality of general probabilistic theories. So I start by giving a diagram of what actually is in my mind, and I hope this is a good outline for this talk. So I will very briefly go over operational formalism and then two mathematical descriptions for this formalism. The first one is ontological models. The other one is GPTs. And then I discuss statistical equivalence at an operational level, and hopefully that should carry over to either of the models that we use, which gives rise to what I call broad notion of non-contextuality. And then I will discuss how general probabilistic theories can be mapped onto ontological models, actually onto non-contextual ontological models. So what do I mean by operational formalism? So usually it's the case, consider a preparation and measurement measure experiment in the lab, and what we have typically is some operational description of what we do in the laboratory to prepare some physical system, and some other prescriptions to do measurements on those systems. And all we have access to basically are just the probabilities of different outcomes given different preparations and different measurements. Okay. So now what we want to do is to make a mathematical description, to give a mathematical description of what's going on in the lab, right? This can be done, of course, in infinitely many different ways. Here I'm interested in just two of them. What we expect from these models is just to reproduce the probabilities that we observe. The first way to do this is via what we call ontological models, which is basically to assume that there exists some ontic space underlying all physical systems. And what we do within the laboratory is basically to prepare ontic states for the system, and what we observe via measurement is basically some indicator function over that ontological, over that ontic space. As you can see, it's assumed that these ontic states and indicator functions are just probability measures, and of course, to get the probability of a certain outcome in a certain measurement of some certain preparation is simply given by this Bayesian rule of probability theory. The second formalism that we can use is what we call GPTs, and the main idea is that if the only thing that I need to explain is the probabilities, then there is no reason to assume that I have to represent preparation or measurements via probability functions. I can use any object, any mathematical object here or here, as long as I reproduce the probabilities. One way to do that is to assume a vector space underlying physical systems. This vector space has an inner product, it has a zero and a fixed unit element. These properties of the vector space actually lets us define a notion of positivity. Using that positivity notion, we can correspond measurements onto vectors over this vector space. Okay, so we want a measure, a probability measure, which is not real valued, rather it's vector valued. And of course, naturally, we wanted to satisfy some sensible properties. For example, it has to be positive for certain event. The corresponding vector should be the unit measure, the unit vector of the vector space, and for mutually exclusive, for the union of mutually exclusive events, we want the measure to be corresponding to the sum of individual measures. So we call each E an effect, and a collection of them we call effect space. Of course, just effect space is not enough. We need to map those effects into actual probabilities. The first thing to do is to find a rule for that mapping. How do we do this? We make some, again, reasonable assumptions, 3 of them. For example, this one just refers to the fact that the product of probability rule should apply for any probability P and any probability measure E. The other one is just convexity. These are natural. Given this, we can state a Gleason-like theorem, which states that any measure that we can define on this set of effects is just basically can be written as an inner product of the effect with some fixed vector A. Okay, so this is very typical thing to do. I won't bother you with the proof. It's very simple. You can read it in the paper. Okay, once we have a Gleason like theorem, so we have the rule for assigning probability measures to effects. We still need some further assumptions to define our status. One such an assumption is the no restriction hypothesis, which basically says that whatever measure that you can define on the set of effects is physically valid, and you can realize it physically. So with this assumption, you get another cone for the status space. So basically, it turns out that the status space is just a dual to your effector spaces. Okay, of course, you can relax this no restriction assumption, which is basically just putting some further restrictions on the set of states. Then you get a smaller status space, or you could put some restrictions on the effector space and get a smaller effector space. These restrictions can be anything physical or information theoretic or whatever you like. This is not something that that we consider here. What you get after putting these extra restrictions is something that we call sub-GPTs, or in some literature it's called fragments of the theory. So now we have 2 different models that we can construct for our operational descriptions. Now we add some more structure to those. The first thing we do is something which is known as a statistical equivalence assumption. So it says that if you have 2 different preparations that gives you the same statistics for all events in all measurements, then those preparations, those ways of preparing states in the laboratory are physically equivalent. So this is an assumption at the operational level. So this splits the set of all preparation into equivalence classes, and every element within an equivalence class, we just call it a context, a preparation context. You can also assume a statistical equivalence for measurements, and you get equivalence, measurement equivalence classes. But what I'm more interested in is the following assumption, which states that if you assume a statistical equivalence for measurements, then what you would like to have is to carry over that assumption over to your mathematical formalism. So whatever mathematical formalism you use to model what's going on in the laboratory, then you want that also to satisfy this statistical equivalence assumption. This is what I call broad non-contextuality. And what it means is that, for example, if you're using GPTs, then two equivalent preparations, operational preparations, must be represented by the same state vector within your GPT. The same for measurements, they must be represented by the same effect vector. And this is so natural that it's already within almost all theories we have, including the standard construction of GPTs. Now, what happens if we also impose that assumption onto ontological models? We get something that we call a non-contextual ontological model. In this case, when you have two operationally equivalent preparations, you should represent them with exactly the same probability distribution over the ontic space, and the same for measurements. One very important thing here is that these functions, mu or xi, they should be unique because, for example, if I can have two different functions for P1 and P2 that are statistically equivalent, then there is nothing extra, without no extra assumption, there is nothing to prevent me from assigning P1 to mu and P2 to mu prime, for example. So in this sense, I will violate the assumption of broad non-contextuality at the ontological level. Okay, our goal is to determine which GPTs can be mapped to non-contextual ontological models, which means that, okay, this is operational description, this is the GPT, and this is the ontological model. Can we construct these two maps that map states to ontic states and effects to indicator functions? The first result is that if we assume the no restriction hypothesis, that is for the maximal, the largest GPTs that we can have, then the result is that the preparations should be a simplex in the vector space that contains the GPT. Of course, it follows via the no restriction hypothesis that the measurements should be the dual to that state space. I won't go through the proof, but I can give you an intuitive reason why this should be the case. So basically what no restriction hypothesis tells you is that it tells you to bring in whatever measure that you can. Okay, so if you're going to bring in whatever probability measure you can, the sharpest you can go is to go with the direct delta measures, and this gives you the fact that basically the extreme points of your GPT must be represented by direct delta measures, because this is the farthest you can go. Okay, now if I have an overcomplete set of extreme states, then and they are, because they have to be represented by direct measures, then what happens is that I will automatically get some mixed states like here, which do not have a unique decomposition into these extreme points. This means that you're violating the broad non-contextuality assumption. And this is an intuitive proof why, if you assume the no restriction hypothesis, you basically restrict your GPTs to be simplex. You cannot have overcomplete extreme points. What happens if we relax the no restriction hypothesis? Well, this was the maximal state space. Relaxing this just means that you have to choose a smaller set, but it is evident here that in this case, overcompleteness is not a problem, because I can have an overcomplete basis and still express them in terms of, you know, the complete set of Dirac measures that I should have for a maximal GPT. What happens is that you can prove that you will get a non-contextual ontological model for the sub-GPT if and only if you can fit it, you can embed it within a GPT, a larger GPT. But one important point is that you have to keep the dimensionality. You cannot change the dimensionality. And I will explain that by the next example. So this is the probability table for a rabbit theory, which basically is a qubit where you constrain your states to have real entries in the density matrix. The most important thing to note is that once I talk about a sub-GPT or a GPT, what I'm assuming is that there is nothing else beyond this table to be measured within the laboratory. There's nothing beyond this possible, okay? Of course, I mean modulo convex combination of these or, you know, coarse graining of the effects, but this is the finest table that I can get. Now, if I want to construct a theory for this table explaining the data, the first thing I do is I check the rank of this table. The rank of the table is 3, and it tells me that the minimum dimensionality that I can use to construct any theory is 3. Here is an example of a 3-dimensional representation of states and vectors that reproduce this table, right? Okay, but it's pretty easy to see that if you want to map this theory to an ontological model, it's impossible. Because if you want to go to 3 dimensions, then you have to have all these entries positive. But this is not possible because you have 4 vectors and you only got 3 dimensions. It's easy to check that this is impossible, but of course, you can play the trick, increase the dimensionality, and go to dimension 4 with these extreme points for your ontological space, and then represent your theory like this. If I show it on this picture, you see this corresponds to this square, right? And potentially, you immediately see the problem here. Notice that you are restricted to having this set of measurements. So with these measurements, what you see is that you have 2 different states. You can find 2 different states that produce exactly the same statistics. Okay, so this means that you have a statistical equivalence at the operational level, while you can violate that equivalence at the ontological level. Therefore, your ontological model does not satisfy the broad non-contextuality, so you cannot have an ontologically non-contextual ribbit theory. So that was pretty much it. Here is a diagram of what we can do. Again, this is something that goes on in my mind. So the interesting question would be, what happens if I take a GPT and remove this broad non-contextuality that is already included in the construction? Or on the other hand, I can consider ontological models where I remove the positivity. And what I expect to get at the end is by removing all these unnecessary assumptions, we should be able to get some high-level mathematical construction, which is, free of any assumption. And once you add these extra assumptions, you recover GPTs or you recover ontological models, depending on what assumptions you impose. So with that, I would like to thank you. And if there is any questions, I would be happy to answer.
Thanks very much. That's a particularly interesting talk. Actually, is it possible to go back to your oh, I'm looking for the languages I want in there. But is it possible to go back to your last slide so that we can see this kind of mind map as we ask questions? Yeah, I'd like this one. So we have, sure, I need to launch the applaud, of course. Okay, so let people applaud and ask their questions over on Slack. So let me, so it just starts by kind of a question that occurred to me as I went along. I'm not aware of people having looked at Gleason type theorems in the setting of GPTs before. Was there actually work on this before?
I'm not aware of any published work, but John Selby once told me that there was a talk at Perimeter Institute by someone that I forgot her name, and they have something similar to that Gleason type theorem that I'm stating, but probably more abstract and a little bit more sophisticated from a very different perspective than what I have here. What I have here is just let's say it's pretty a standard Gleason-like theorem. It's the proof and the assumptions. It's pretty like what Caves and Bush did back in the old days.
Okay, so actually John has just shared the paper with us already. So it's from Victoria Wright and Stefan.
Oh, that's great.
Maybe mispronouncing names, but yeah. Okay, nice, interesting. Yeah, because it seems like a very nice and natural idea, but I don't recall having seen this kind of thing before. Okay, so I'll hop over to some questions from the Slack channel. Vilazny asks, is there a notion of post-measurement state, or is there a post-measurement state update rule in GPTs? Or would this be an additional structure that would actually allow
I think there exists one such a notion in the standard GPTs, in standard GPT construction. I think there is an state update rule, but that's not what I considered.
Okay, fair enough. So actually, I see there's quite an active thread of replies on this, but it probably won't have a chance to skim through all of those.
I should get there and read and yes.
Yeah. Okay. So another question from Stefano Gogioso. So he asks, can you briefly comment on the overlap between the notion of contextuality that you're discussing and the notion of contextuality described in the sheaf theoretic framework of Abramsky and Brandenberger and others?
So what I'm introducing here basically is nothing new, right? It's just a slight tweak to the generalized non-contextuality of Robert Bacon's. Yeah, that's basically it's basically the same. It's just that I have carried this notion of a statistical equivalence at the operational level and extend it down to whatever descriptions that you want to have. Yeah, I don't know if that answers the question.
Well, yeah, okay. I guess I'll let Stefano take it up with you over in the Slack if he wants to follow up on it. Okay. Okay, so maybe a last question from to indulge my own curiosity and try to stamp out some of my own ignorance. So I'm trying, when I look at what you're doing, so it seems like you're bringing these kind of equivalence assumptions to play now in GPTs. And so I'm kind of trying to put it together in my head if there's an intuition behind this of trying to interpret the GPT as a kind of ontology in itself, or is that completely the wrong way of
So my intuition is that no, I wouldn't go as far as to say that GPT is ontological on its own, but what I suspect is because I was trying to do this, and What I suspect is that once you remove the positivity from ontological models, you get into something GPT-like. So in a sense, ontological models for me look like GPTs with the extra positivity restriction.
Yes, okay.
But of course, the converse is not true. Plus, at the ontological level, you have this specific interpretation that you cannot necessarily preserve it for GPTs, because if you go beyond single systems, like you go for a combination of two systems or more, then you probably will run into the interpretation, the standard interpretation problems, like locality, etc., etc. What I have in mind with this particular figure here is that it might be possible that if you remove all these extra assumptions on both sides, you get to something to a unified model, something fixed, that you can recover ontological models or GPTs from that, let's say, less restrictive model.
Okay. All right. So at that, I suppose I will invite people to continue the discussion and keep posing their questions or follow up with Farid over on the Slack channel. And I'll thank Farid again for a fascinating, really interesting talk here.
Thank you.
Thanks very much again.
Thank you.
Thank you. My own, since I'm the only one who can. So thank you again. So at that, we'll move on to the next talk of this session. Thanks, Farid.
Sure.